Hi, my name is Peter Andriska and I'm the head of research at Level 5. In this talk, I would like to tell you about machine learning planning and simulation my team is working on. So what I will cover is my views on the limitations of the current self-driving technology that is adopted across the industry. And then I would like to tell you about the Autonomy 2.0, which is a machine learning first approach to solving self-driving. And that is composed of three key pieces: machine learning planning, machine learning simulation, and large-scale data collection. And what I would like to convince you about is that this is a very promising approach we should be all going towards to. Before we dive in, let me tell you a little bit more about Level 5. So we are part of Lyft, and now we are becoming a part of Toyota Woven Planet. We have more than 300 people across California and London. We are operating our in-house fleet of autonomous vehicles, and we are working towards development of L4 and L5 self-driving technology. What we are also doing, we are organizing a tutorial on the data-driven autonomy, which is very much something I will be talking about here as well. So if you want to learn more, please just visit www.selfdrivingcars.org and you can hear more there. So let's dive in. So I would like to start telling you a little bit more about how the self-driving cars work today. This is a self-driving car that has a number of sensors, cameras or lidars that allows us to see the world. And the first thing to do anything for self-driving car is it needs to understand what's around it, which means like the position of other cars, cyclists, pedestrians, position of other lanes or traffic lights. When it knows what's around it, the next task is being able to tell what's going to happen, which means where is everybody going, such that you can predict the future. And when you know that, the car plans its behavior, which is motion planning. And finally, this plan is executed, and the entire cycle repeats again. When you look at this stack, and you look how much machine learning is used in these individual steps, what you discover that in the current technology that is widely adopted across the industry, the amount of the machine learning is used, but not to solve each step. In particular, perception is more or less machine learned, but when it comes to planning and simulation, this is still very, very handcrafted solutions. Just to understand then why, when the car is planning the behavior, the most usual approach that is used is optimization of expert-based cost function. You are trying to find the trajectory that keeps the vehicle enough space. It sticks to the middle of the lane. It trades off different cost factor about comfort and safety. And this generally works. But one big disadvantage is that it's very difficult to scale and to new scenarios. And moreover, this process needs to be repeated for each new geography. Furthermore, testing of the stack is also takes a lot of time on the road, which is expensive and limits the speed of iteration. On the other hand, Autonomy 2.0 is a machine learning first approach to self-driving that is trying to solve all pieces using machine learning, which is mostly in the space of solving planning and simulation using machine learning techniques. And finally, to power all these algorithms, we need a lot of data. So how do we get all this data? And we're talking about that in a bit as well. But it has a number of benefits. So instead of handcrafting the behavior of what the car should do, this behavior is learned from the human demonstrations, which is much more scalable approach. And testing can be then mainly offline using machine learning simulation. Given this, a significant benefit is that the performance of the system increases the more data you are training on. And what it also allows you to do is to build the entire stack just once and then deploy it many times. You just need to collect different data from different countries and retrain the model. And that allows very rapid scalability across different geographies. So this would not be possible with Autonomy 1.0. Okay, now let's talk about each of these three elements: machine learning, planning, and simulation, and data collection in turn. As discussed before, handcrafting the behavior of what the car should do is very expensive and has limits in the complexity of situations that you can handle. So what you can do instead is to train a neural network that learns from human demonstrations to drive the car. It looks something like this. You are feeding the network the input what's around the car. This is coming from the perception and the HD map of the area, and the network is producing the steering command of what the car should do. So to make the thing safe, we are also applying a safety net that limits the behavior of what the car should do only to the safe ones. And there are many different ways how you can train this network, ranging from imitation learning, perturbation training, or closed loop training, that I won't be able to go into details of due to the time. But the main takeaway is that the more data you are training this system on, the better it works. And that's one of the big benefits. To see this, then here is a system that was trained only on 3.5 hours of human data. And you can see that even with this little data, the system can actually already keep the lane and drive in it. When you though add more data and you train on 1,000 hours, what you see that the behavior is more stable, and but generally already like this simple behavior can be learned from just little data. The situation gets more complicated with the complexity of scenarios. So here is a car that is coming to an intersection behind another car, and as you can see, it cannot handle stopping towards the lead car. But as you train on more data, then this behavior is successfully learned, and the car can wait for the green light and then just follow through the intersection, keeping the safe distance to the car in front of it. Here is another example. This is waiting for traffic light on an intersection again. And the network is not sure when to start moving, and that leads to a collision. And as you train on more and more data, this behavior is successfully learned. And as I said, none of this is actually scripted or engineered by the engineers. This is all learned from the human drivers. Next, this is how it looks when you put it on real cars and let the network drive a real car. So here is a scenario where the car is nudging to the row of cones that are blocking the way, and this is also learned from the demonstrations captured in the world. Here are a few more examples that of handling unprotected left turn, handling the cut-in, and also nudging around the vehicles. And this is something that we do. We are improving the performance of these systems. There is still several open questions. What's the best way how to train machine learning planning systems such that they scale and deal with the complexity of the real world, but this is very, very promising. Okay, let's talk about machine learning simulation, which is one of the components of Autonomy 2.0 stack. To understand this, let's first explain how the self-driving testing happens today. It starts with identification of some feature or block that you want to develop. that you implement, and then you test it on the road to see how well does it work. And based on that, you debug whether it's working or not working, and that informs you to make changes. The problem with this approach is that it's extremely expensive and scales very poorly. And also it's not reproducible, which makes this testing very difficult. Until the same situation happens on the road again, it takes a while. So instead, the question is, how can we best test the performance of self-driving technology offline without the need of much road testing? This doesn't mean we will not need any road testing, but it's much less important in the development cycle. So what is simulation? So simulation is basically ability to replicate the real world experiences that you would encounter on the road offline without actually needing to go there. So this is the view at the how the self-driving car sees the world around itself, as you've seen before. And the goal is to be able to replicate these kind of experiences, both the usual and unusual, and see how the self-driving car performs in these situations. The most naive approach that is widely used is called log replay, that you take a piece of a recorded scenario that actually happened on the real world, and you basically replace the behavior of the car with the new behavior that you developed and see what happens. The problem with this approach is that the environment is non-reactive, which means that if your behavior is different to the one that you actually did on the road, other cars or pedestrians don't react to it, which makes the evaluation very difficult. You can make it better by scripting the behavior of other agents, or use a simulator that already exists, such as Carla, to get the reactive behavior from other traffic agents as well. But the problem is that this doesn't scale in terms of complexity. You cannot script all the possible situations that everybody might do or that might happen. So our approach that we are using at level 5 is we believe that the only way that we can achieve very realistic level of simulation, we basically have to learn it from the real world. And this way we can bridge the gap between the reality and the simulation. We recently published this work at the ICRA, so please feel free to check it out. I will provide you a very brief overview how does it work. So you can train a neural network on historical observations and get it to predict the future. And this, you take a bunch of data, you run it on a cluster of computers to train a neural network, and you get your neural network that you can then use for simulation. And then during the testing, you basically replace every agent with this neural network and get the neural network to control that agent during the simulation. And this is pretty simple, and it works surprisingly well. So just how it works, so you start with some initial state, and basically then in every step you use neural network to control all other cars as it seems in the real world. So here are some examples how are we using this. As you can see, like these are all synthesized scenarios. These are not real logs, and each agent is controlled by a neural network. And you can see that the behavior is almost indistinguishable from the one that you would actually see on the real road, even though like this is completely synthesized scenario. So you can see that if there is a red light, that the traffic for that lane stops, nobody's moving, and you can also see that the cars are following the lane, etc. And none of this was scripted. This was all learned from the real-world demonstrations. And what we also observe is like it works better and better the more data you are trained in this zone. And this is very promising because to improve the performance, all you need to do is really to collect more data and get better simulations. So I hope that by now you are convinced that machine learning planning and simulation is a really promising approach that scales its performance with the data rather than with engineering, and that has many benefits. So the logical question then is, where are we going to get all the data to train these systems? And we will likely need to collect millions of miles of driving to see all different situations and to learn from them. If we were today to scale the current hardware to collect all this data, it would be very expensive. So the question is, can we use cheaper and low-cost commodity sensors to get the value out of them? And this is indeed an open question. But one of the benefits of having the fully machine-learned self-learning stack, you can answer these questions empirically by running experiments. And that's what we did. So here's an experiment that we also published at ICRA this year, where we took the data from the high fidelity self-driving sensors that contain LiDAR cameras and radars, and we decreased its performance by reducing the quality. But what we did, we increased the quantity. We trained on much more data of that type. And what we saw is that the performance of such system is better despite it's being trained on lower quality data than just training on a high quality data coming from, but in lower quantity. So this is very promising, and it says that perhaps we can relax some of the requirements in order to be able to collect large data sets and to use them for training Autonomy 2.0. So in summary, what I wanted to show you in this presentation is some of the work that we are doing on machine learning planning and simulation, and that is very promising approach that we believe can solve many of the current issues of the current technology that is used in industry, and that also that we need large-scale data sets to train all the systems. So I would like to conclude with sharing with you 3 resources if you want to go deeper and help us solve these different problems that are still there to solve. We recently open sourced a 1,000-hour prediction dataset, which is the largest dataset of its kind and that can be used for training machine learning planning and simulation models. We also released an L5 kit, which is an SDK that allows you to train these models using the dataset. And it also contains a number of baselines you can take as a starting point. And as I said at the beginning, we are also organizing the tutorial where you will see videos from people working at level 5 talking about different parts of the self-learning stack, and also contain hands-on sessions where you can try to implement your own solutions. So please check it out.